Welcome back. So today we are going to be adding 3 new items to your physics everything sheet. Just to refresh your memory, last time we had talked a little bit about potential energy and kinetic energy. So these two in blue are already on your physics everything sheet. But since we're going to talk about different types of energy today, I just wanted to refresh your memory. So first, potential energy. Due to gravity, PE sub G, you can use the equation PE equals mgh, the unit is joules. Kinetic energy is due to motion, and that equation is 1/2 mass times velocity squared. And again, the unit is joules. All energy has the unit joules. Okay, so now we're going to add in a couple different new types of energy. We're going to add in spring potential energy and thermal energy. But before we're able to add spring potential energy, we want to introduce a spring or an elastic object so that we can talk a little bit about its spring constant and how it holds some spring potential energy. So let's start with the idea of spring constant. So spring constant is abbreviated with the letter K. It's a lowercase k. And the spring constant represents how rigid or how resistant to expanding and contracting an object is. So this rubber band, it expands and contracts pretty easily. It's not very resistant. So it has a spring constant, but it's going to be a relatively small value. I can solve for the spring constant by taking the force applied on the spring and dividing it by the distance that the spring moves when that force is applied. So for example, if I take this spring, this rubber band, I apply a force to it and I measure that force using my spring scale, and I note it stretches an extra 10 centimeters when I apply a force of 4 newtons. I could say the force 4 newtons divided by 0.1 meters or 10 centimeters gives me a spring constant of 40 newtons per meter. Now the spring constant only works within the bounds that the object can stretch. So this one, it can go from here out to here. So that's a stretch of maybe 20 centimeters, right? Outside of that realm, I can't stretch it anymore. So the spring constant stops making sense, because then if I keep stretching it, the rubber band will break. So it's not forever, but it's as far as the object can reasonably stretch. All right, the unit for spring constant, well, force is in newtons and distance is in meters. So the spring constant is newtons per meter. And then general rules of thumb to remember when we're thinking about a spring constant is that the more rigid or the stronger, more resistant to stretching the spring is, the higher the K value. So for example, the shocks on your car, you can look under there and you see a big metal spring next to each wheel if it's an older model car. Those would have really high spring constants because you got to put a lot of weight on that in order to compress it or expand it. Then F stands for the force applied to the spring, and D is the distance moved by the spring due to the force. All right. Next piece, spring potential energy. So spring potential energy, we're going to abbreviate with PE, spring. And the spring potential energy is the energy stored in an object due to its expansion or compression. So springs can work in both ways. I can compress it or expand it. And either way, I'll be storing some energy. So if I push down on a spring and then release it, it pops back out. I'm storing the energy in the spring. If I pull it apart and then release it and it snaps back, that's expansion storing some energy. And this can also be called elastic potential energy because it's due to the elastic nature of an object. So spring potential energy, we can use the equation 1/2 kx squared, where k is the spring constant and x is the distance that the spring is stretched during that time that it's holding the potential energy. Okay, so x would be how far it goes, and that's added over here in my notes. K is the spring constant, x is the distance the spring is stretched. And the unit for spring potential energy is joules, represented by capital J. So if we want to prove that it's joules, I could say spring constant is newtons per meter, and then x is in meters because it's a distance squared. So newtons per meter times meters squared. The meters cancels with the meters, and I'm left with newtons times meters, which is equal to a joule. And all energy has the unit of joules. All right. And then finally, our last thing that we're going to add today is thermal energy. And we're going to abbreviate thermal energy TE, T for thermal. You could also sometimes see it written as E sub TH, so that could work too, energy thermal. Thermal energy is energy that is lost to heat. And actually, I'm going to stop and correct myself. It's not really lost, it's transferred, because remember, energy is neither created nor destroyed. So I'm not losing the energy, I'm just transferring the energy from another form into the heat form. Okay, so thermal energy is the heat, and this largely comes from friction. So thermal energy comes from friction as objects are rubbing together or expanding and compressing, they're creating heat, and that's our thermal energy. So thermal energy is also represented in joules. So the unit, again, is going to be J, joules. And thermal energy is equal to the total energy, how much I started with, minus whatever potential energy still exists, minus whatever kinetic energy still exists. Because energy is neither created nor destroyed. So the total energy is going to be equal to the potential plus the kinetic plus the thermal at any given point. Right? Whatever total energy was in the system has to stay the same, and these are the types of energies that we know about, so these are the types of energies that would account for that total. And then if I just solve for thermal, pull that over, subtract out potential, subtract out kinetic, it would be total minus potential minus kinetic gives me thermal. All right, so notes on this one. The big note is that thermal energy is always increasing. And this is due to the principle and concept of entropy. So entropy is a measure of disorder. And heat is the least ordered form of energy because it's just molecules moving around really fast. That's when you feel heat. It's because molecules are moving quickly. So over time, everything moves from ordered, like in place, potential energy, kinetic energy, to less ordered or to disorder. What that means is that all energy eventually shifts over to thermal energy. So if I have potential energy, eventually that thing is going to fall down, it's going to hit the ground, there's going to be some friction, and it'll turn into heat. If an object is moving, eventually it'll counter friction or it'll run into something, and it'll turn into heat. So all energy eventually goes to thermal energy, and this is the process called entropy or disorder. Awesome. Okay, so those are our three new concepts. Spring potential energy based off of a spring constant, and thermal energy. And then we've also talked about potential due to gravity and kinetic energy. Wonderful. Glad you've got those added. Now we can start working with those types of energy as we create some vehicles.